Hello there. So, in continuation with our discussion, we're already on the last topic for our chapter, thermal stress. So, what is this thermal stress? Actually, thermal stress is the stress produced from the expansion and the contraction of a particular body when subjected to temperature changes. We all know that an increase in temperature results in expansion, whereas a temperature decrease produces contraction. If you can recall your knowledge in chemistry, if there is an increase in temperature, the molecules in the body tends to move further away from each other. And during a drop in temperature, molecules will move closer to one another, therefore producing a contraction to the overall body. This deformation is isotropic. So what do you mean by isotropic? The amount of deformation is the same in every direction. So it's the same in the x direction, the y direction, as well as the z direction, and proportional to that temperature change. As you can observe later, the formula is in the first degree. So the formula for thermal strain is given by epsilon T is equivalent to alpha times delta T, where your alpha is the constant known as the coefficient of thermal expansion and delta T is the temperature change. The coefficient of thermal expansion represents the normal strain caused by 1 degree change in temperature. You already have encountered this property in your surveying. So, in your surveying, during your measurement and your layout, you are actually asked to determine the error from a temperature change. And one property there is the coefficient of the thermal expansion. Delta T is taken to be positive when the temperature increases and negative when the temperature decreases. So this would be our sign convention if you will be using the formula. Since a positive temperature produces elongation, then we will have a positive sign and a negative sign if there is a drop in temperature since it produces contraction. The units of alpha are per degree Celsius in the SI system and per degree Fahrenheit in the United States customary system. Typical values of alpha are 23 times 10 to the negative 6 per degree for aluminum and 12 times 10 to the negative 6 per degree for steel. So these are the commonly used materials, especially steel. If the temperature change is uniform throughout the body, the thermal strain epsilon T is also uniform. So consequently, the change in length in any dimension L of the body is given by the deformation due to the temperature change is equivalent to the thermal strain times the total length, or that's equivalent to alpha times delta T times the length. If thermal deformation is permitted to occur freely by using expansion joints or roller supports, no internal forces will be induced in the body. There will be strain but no stress. So there will be deformation, but actually the member is stress-free. Cases where the deformation of a body is restricted, either totally or partially, internal forces will be developed that oppose the thermal expansion or contraction. The thermal stresses caused by these internal forces are known as the thermal stresses. Okay, since the bar is not allowed to elongate or contract, internal forces will develop in the form of tension in the case of elongation and compression in the case of contraction. Forces that result from temperature changes cannot be determined by equilibrium analysis alone. That is, these forces are statically indeterminate. So if we are solving thermal stresses, we will also apply the principle of statically indeterminate problems. The analysis of thermal stresses follows the same principles of statically indeterminate problems. So first, determining the equilibrium equations, followed by determining the compatibility equation and applying the Fox law. So the only difference is the inclusion of the thermal expansion. Okay, so this is now the procedure for deriving the compatibility equations. So number one, remove all constraints from the body so that the thermal deformation can occur freely. This procedure is sometimes referred to as relaxing the supports. Then, show the thermal deformation on a sketch using an exaggerated scale. The next step is apply the forces that are necessary to restore the specified condition of constraint and deformations caused by these forces to the sketch that was drawn in the previous step. Draw the magnitudes of the deformations so that they are compatible with geometric constraints. And then by inspection of the sketch, write the relationships between the thermal deformations and the deformations due to the constraint forces. Now let us try to solve a problem in thermal stress. So for our problem 1, we have a horizontal steel rod 2.5 meter long and having a cross-sectional area of 1,200 square millimeters. Is secured between two walls as shown in the figure. The rod is stress-free at 20 degrees Celsius. Compute the stress when the temperature has dropped to negative 20 degrees Celsius. For this problem, we will be considering two situations. The first is that we're going to assume that the walls do not move. In other words, we have a rigid supports. And then the second situation is that the walls move together a distance of 0.5 millimeters. So for the second case, we have a yielding wall. So we'll be using the coefficient of thermal expansion equivalent to 11.7 times 10 to the negative 6 per degrees Celsius and 200 gigapascal. Okay, so we're already in our MATCAD worksheet. So we'll begin now solving the problem. So first, uh, we'll define our variable. So that definitely we'll have the deformation due to the temperature change. So we will assign delta t as the thermal contraction due to a drop of temperature. Okay, so there is actually a 40-degree drop in temperature. And because of this thermal contraction, and since the bar are secured to the supports, there is a restriction. Definitely, this will produce the stress on the bar. And let's say this delta P is the elongation, oh no, yes, the elongation caused by the tensile force in the bar. Okay, so these are our variable. Okay, so let's start with the first condition wherein the walls are rigid. Okay, so I will be inserting a sketch for the problem. So we have here the sketch. If we're going to understand the scenario of the problem, the bar is attached to rigid walls. So both ends of the bar are attached to the rigid wall. And then the initial temperature is positive 20 degrees Celsius. And at the same time, the bar are stress-free. The bar is stress-free. Now, if there is a drop in temperature, the bar will contract. In other words, it will have its length reduced. So the length would be smaller than 2.5 meters. But since it cannot undergo contraction because it is secured onto these rigid walls, it will have a stress, a tensile stress to be specific. Because after contraction, we have a shorter length. Actually, if the bar is allowed to contract, they will have a shorter length, but since it's not allowed to contract, it maintains the same length. Therefore, the bar now will be in tension. Now, this situation is similar if the bar is allowed to deform. So to do that, we need to remove one of the support. So having the support removed, the bar now is able to contract after the drop of temperature to minus 20 degrees Celsius. And this value is the delta T. And then, to bring back the bar to its original position, that is, to attach the bar back to the wall, we're going to apply a force P stretch this bar to attach again to the wall. Now this force field now will produce a tensile stress in the bar. Okay, so by looking now at the picture, it is obvious that the deformation due to the change in temperature, the contraction bar is actually equivalent to the deformation in the bar caused by the force. So there we have the compatibility equation. So all we have to do now is to substitute the values. Okay, so the deformation due to temperature is equivalent to your alpha, the coefficient of thermal expansion, times the change in temperature times the total length. Okay, and that's equivalent to the temperature or the elongation in the bar. So that's equivalent to the stress in the bar multiplied by the length divided by the modulus of elasticity. Okay, since they have the same length, we can cancel L. So the formula now is reduced to alpha times delta T is equivalent to sigma divided by the modulus of elasticity. Since we're after with the stress, okay, rewriting the formula, we have now the stress is equivalent to your alpha times delta T times the modulus of elasticity. So we already have the expression to solve the stress. All that's left is to substitute the value. Our alpha is equivalent to 11.7 times 10 to the negative 6 per degree Celsius. This is per degree Celsius. And our delta T, so that is from 20 to negative 20. So we have actually a drop of 40 degrees Celsius. And our modulus of elasticity is equivalent to 200,000 MPa. So taking note of the unit. So your alpha is actually per degree Celsius. Your delta T is in degrees Celsius and your E is in 200,000 megapascal. So the stress now And the stress is equivalent to your alpha times delta T times E. So we have now a value of 93.6 megapascal. So for situation A, wherein the walls are rigid, the stress in the bar will be 93.6 megapascal. So we're now on the second situation wherein the walls move together by an amount of zero point 0.5 millimeters. So to have a better understanding of the problem, we will insert this prepared sketch. Okay. So initially, the bar is fastened to the walls. And then, using the same approach that we had in the previous problem, we detach the bar from the wall so that it can undergo thermal contraction. So, the drop of temperature, the thermal contraction of delta T is observed. Then, to attach the bar back to the support, we need to apply a force P. And this force P will produce your delta P to attach that to the wall. But this time, the wall moved an amount of 0.5 millimeter closer to the bar. So your force P will only produce a deformation up to this portion. So you have smaller value of force compared to the previous situation wherein the walls are rigid. So from the picture, we can already determine the relationship of your thermal contraction to the contraction due to the tensile force P. So your thermal contraction delta T is equivalent to your delta T plus zero point 0.5 millimeters. Okay, so let's substitute the value. So delta T is given by the coefficient of thermal expansion times delta T times the length equals to the stress times the length divided by E plus zero point 0.5. Solving for the stress, we have the stress is equivalent to we have alpha times delta T times the length and minus 0.5, and it should be multiplied by the modulus of elasticity, and then divide by the total length. Okay. So we have the expression for the stress, and substituting the values, we have now 11.7 times 10 to the negative 6 times 40 times 2,500 millimeters minus 0.5 millimeters, and times 200,000 megapascal, and divide by 2,500. So we can now determine the stress in the bar, and that's equivalent to 53.6 megapascal. So as you can see, we have a smaller stress of 53.6 when the walls move together the amount of 0.5 millimeters compared to when the walls are rigid. Okay, so we're now on problem number 2. Let us read the problem. The figure shows a homogeneous rigid block weighing 50 kilonewton that is supported by three symmetrically placed rods. The lower ends of the rods were at the same level before the block was attached. Determine the stress in each rod after the block is attached and the temperature of all bars increases by 38 degrees Celsius. Use the following data. For each steel rod, the area is 480 square millimeters. The modulus of elasticity is 200 gigapascal, and the coefficient of thermal expansion is 11.7 times 10 to the negative 6 per degree Celsius. For the bronze rod, the cross-sectional area is 960 square millimeters, 2.7 gigapascal for its modulus of elasticity, and the coefficient of thermal expansion of 23 times 10 to the negative 6. Okay, so let us move now to our worksheet. Okay, so the first step is to determine the equilibrium equation. So we need to write the equilibrium equation, and we can do this by extracting the free-body diagram from the figure. Okay, so we have here the free-body diagram. The forces acting on the block is the weight of the block, which is equivalent to 50 kilonewton, and the tensile forces in the rods. So let PST be the tensile force in the steel rods, and PBR be the tensile force in the bronze rod. So applying the equations of equilibrium, the best that we can use here is the summation of forces along the y-axis. So applying that equation, so we have now summation y is equivalent to, we have two steel rods, so we have 2 times PST and PBR. Of course, minus 50 kilonewton. And since we need to have a consistent unit, it's better for us to convert kilonewton into newton. So we will expressing our answer in terms of newton for the force. For the length later on, we will be expressing the length in terms of millimeters, so that we will have the base units of newton and millimeters, and we can determine the stress in terms of megapascal. So here, instead of 50, we'll have it 50,000 newton. Okay. Since this is in equilibrium, this should be equivalent to 0. So our equation now would be 0 is equivalent to 2 times PST plus PBR minus 50,000. Okay, so let us rewrite the equation. So we have now 50,000 is equivalent to 2 times PST plus PBR. Okay, so that would be our equation. But since we are asked to determine the stresses in its rod, so it's better to express forces in terms of the stress. And we can do that using Hooke's law. So we have 50,000 is equivalent to 2 times PST is actually equivalent to the stress in the steel multiplied by the area of the steel. Okay. Then plus your PBR is equivalent to the stress in the bronze multiplied the area of the bronze. And we know that our AST is equivalent to, okay, we have 480 square millimeters squared. And for the bronze, we have 960 square millimeters. So we need to substitute the value to the formula. So we have now 50,000 equivalent to 2 times 50 times 480, then plus the stress in the bronze multiplied by the area of the bronze, which is equivalent to 960 mm squared. Okay. So let us further simplify the formula. So we have now 50,000 equivalent to 2 times 480. So we have 960 times ST plus 960 times stress and volts. Okay, so we have now our equilibrium equation, and this would be our equation 1. Next is we need to determine our compatibility equation. So we will derive the compatibility equation from the metric relationship. Okay, so I already have the sketch. What would happen to the rods when they are applied by a block, a force from the block which is 50 kilonewton, and also a rise in temperature of about 38 degree Celsius. Okay, so let's move to the next page. So that would be the most likely behavior of the rods. So if you have an increase in temperature, you will have an increase in length of the rods. So the steel rods will elongate by this amount, and also the bronze rod will elongate by this amount. So definitely, because the coefficient of thermal expansion for the bronze rod is greater than that of the steel, we'll be expecting a much more uh, greater amount of deformation due to the temperature. At the same time, because the rods are carrying the block weighing 50 kilonewton, they will be subjected to a tensile force that will produce elongation. So the steel rod will produce this elongation as well as the bronze rod. Okay, but um, because they should be at the same level, the requirement of the problem is they should be at the same level. Instead of having here a tension, we might have a compression because the combined elongation of the temperature as well as the tensile force will be greater than the combined temperature and tensile deformation of that of the steel. So there will be a chance that this will be compression or will have a contraction. Okay. So let us write now the compatibility equation. So from the figure, our elongation T, let's call that one as ST. And let's say the elongation T ST plus the deformation T from tension of the steel is equivalent to the combined deformation of for the bronze. We have delta P dr plus delta P dr. Okay. So this is our compatibility equation, and let us substitute the value. So we have here the coefficient of thermal expansion for the steel times the change in temperature delta T times the length of the steel plus, okay, so we have here the stress in the steel times the length of the steel divided by the modulus of elasticity of steel. So this is equivalent to, okay, the coefficient of thermal expansion for the bronze multiplied by the change in temperature delta T times the length of the bronze plus, okay, we have the stress in the bronze times the length of the bronze divided by the modulus elasticity of the bronze. Okay, so we're going to substitute the value. Okay, so this is 11.7 times 10 to the negative 6 per degree Celsius multiplied by the change in temperature, which is 38 degrees Celsius, multiplied by the length of the steel, which I believe is equivalent to, you have 0.6, 0.6, and in terms of millimeters, we have 600 millimeters. Okay, so this is plus the stress in the steel, okay, times the length of the steel, 600 mm, and divided by 200,000 megapascal equals equal to, okay, the coefficient of thermal expansion for the bronze is equivalent to 23 times 10 to the negative 6, 23 times 10 to the negative 6 times the change in temperature times the length of the bronze, which is equivalent to 900 mm, plus we have here the stress in the bronze times the length of the bronze, which is 900, and then divided by the modulus elasticity for bronze, which is equivalent to 82.7, or that is 82,700. 82,700 gigapascal. Okay, so let us simplify our equation. So this becomes now equivalent to 0.267 plus 0.003 stress in the steel is equivalent now to 0.787 plus we have 0.010883 stress in the bronze rod. Okay, so let us solve or let us express the stress in the steel in terms that of the bronze. So we can have the stress in the steel now is equal to 3.62767 multiplied by the stress in the bronze plus 173.333. Okay, so we have now our second equation. Okay, this is our equation 2. Okay, so having two equations, we are now ready to solve for the unknowns. So let's combine the two equations. So let us bring here equation 1. Okay, and then we're going to replace the stress of the steel in terms that of the bronze. So we have 3.62767 times that of the bronze plus 173.33. Okay, so we have that equation. So we can now solve the stress in the bronze. Okay, so if we're going to solve for the stress in the bronze, we will have the value of negative 26.20 megapascal. And using equation 2 to solve for the steel, we have 3.62767 multiplied by negative 26.20 megapascal plus 173.333. So this will give us a stress of 78.288 megapascal. As you can see, we have a negative stress for the bronze. It's because the combined elongation of the bronze now is greater than that of the combined deformation of the steel. So it will now produce a compression because it cannot stretch because it's being restricted by the steel. So it will now have a compressive force inside the bronze rod. Okay, so there you have it. We have the stress for the steel, a positive stress of 78.288 MPa, tensile stress, and the compressive stress for the bronze of 26.20 megapascal.